So just a very quick introduction to the air-sea gas transfer. We're talking about the transfer of oxygen or CO2, okay, or methane, helium, nitrogen gas across the sea surface. Okay, and the starting point for that is Henry's law. Okay, so now what you can imagine that within the atmosphere there's a certain fraction of a gas. Okay? And this fraction of a gas, like CO2 or oxygen, can be expressed by a certain partial pressure. Okay? Partial gas pressure. Alright, so now you have a fluid, okay, and you expose the fluid to that gas for a very, very long time. Okay. After a very, very long time, you get an equilibrium concentration of your gas in the fluid, like in the ocean. And there's a relationship between this equilibrium gas concentration and the partial pressure of the gas in the atmosphere. And the link between these two is called a solubility constant. Yeah, and this little equation, it's the KH here. Okay. So now the important piece of understanding is that this solubility constant depends on the temperature. Okay, the solubility, it depends on temperature. Okay, and if there's some above my head, I move my head away. You can see that for most substances, actually the solubility decreases with temperature. Okay, and it has implications, and the straightforward implication is, so if your fluid is in equilibrium and you heat it up, it actually will release gas back into the atmosphere. Yeah? Or if you move your water into an area where it's colder, where you cool down the surface, means that the water will become undersaturated and you can draw more of the gas from the atmosphere. Okay, so this is a very, very important link in the understanding. Okay, and now how scientists work out how much the flux of gas is called the film model of gas exchange. Again, I know it will be a little bit overwhelming because you see equations in there, but I just want to explain the fundamentals to you. Okay, so how these film models work is like that. So you have a surface mix layer in the ocean, okay, and you have a skin layer. So what you can assume is that the skin layer is at equilibrium with the atmosphere in terms of the gas. Okay, and this is all that's shown here. Yeah, you can work out, you can write down a little formula. Just means the skin layer, which is a very, very thin layer, is in equilibrium. So now the surface mix layer can be either undersaturated or oversaturated. Okay? If it is undersaturated with respect to the concentration that you have in the skin layer, okay, the surface film of the oceans, then it will draw gas from the atmosphere. If it's oversaturated, it will release gas into the atmosphere. Okay, so now the amount of gas that is transmitted depends on this this concentration difference, but also something which we call a piston velocity. Okay, it's a little bit the gas flux across the surface. Have a look here above my finger. It's called Fick's law. It has the concentration difference and the piston velocity, and this coefficient, the piston velocity, strongly depends on the wind speed, plus additional factors like if you have breaking waves. Okay, wave breaking. And this is the film model of gas exchange. And you can apply this model and you can work out the for example, CO2 fluxes across the atmosphere. And this is shown on the next slide. It's a map of just showing you the the sign whether there is a region where the CO2 is uptaken by the ocean or whether CO2 is released by the ocean. You can see a global map, and you can see the regions where CO2 is released and where CO2 is uptaken. Okay? And later on, once you understand what subtropical gyres are, you see that these subtropical gyres are the regions where you move warmer water into colder climates and colder water into warmer climates. And this temperature adjustment actually drives this uptake and release of CO2 in the oceans. Quite fascinating stuff. Okay? Indeed, later on you will learn that also overall the ocean is actually a sink for CO2, for the CO2 released by humans. All right.